Hello, my name is Kevin Roberts, and in this video I'm going to go over what a first-order linear differential equation is, and we'll cover a few methods on how to solve the homogeneous case and the non-homogeneous case of differential equations. Before we start, I'd like to say a little bit about me. I am an undergraduate student at Utah State University, getting a bachelor's in applied mathematics and minoring in physics and computer science. Additionally, I tutor mathematics at the Aggie Math Learning Center here at USU. Firstly, I'd like to express the significance of differential equations and why we want to solve them. In macrobiology, for example, we collect data from, say, COVID cases in Logan. After collecting data, we try to model the data with a differential equation to predict the number of COVID cases in the next year or so. Another good example is for an individual trying to prepare for retirement. The differential equation I've provided is the change of money, M, over the change in time, T. The 0.05 is annual interest rate, and the $12,000 is what the individual puts in their bank account every year. The M0 equals 3,000 is the amount of money the individual starts with in their bank account. I've solved the differential equation below, then below that I input 25 years. So if the individual proceeds to put 12,000 in their bank account with 0.05 annual interest, then after 25 years they'll have about $600,000 in their bank account. The graph to the right shows if the individual does this same practice, then after 40 years they'll have $1.5 million. Notice how the graph increases exponentially. Thus, if you want to be rich, start saving and investing as soon as you can. We figured out this from differential equations. Now I'd like to go over briefly what it means to be first order and what it means to be linear for a differential equation. First order basically means we only take the derivative once of a variable in our equation. Notice that dy over dx is the same as saying y prime. Below are some examples and non-examples of first order differential equations. A linear differential equation is one where we don't have any exponential terms in the variable we're differentiating. Notice the second example has an x squared. This is still linear because we are deriving y and not x. Now, what does it mean to be homogeneous or non-homogeneous? Whenever we can get a differential equation in the form y prime plus pty equals 0, then we can say it's homogeneous. This is essentially whenever we can separate variables t and y and multiply them. A non-homogeneous function is one where we cannot separate functions containing t and y, and I'll show this more explicitly in the next slide. In summary, if we can manipulate our differential equation to look like either of the equations above, we say it's either homogeneous or non-homogeneous, where pt and qt are both functions of t. Notice that they also don't have to contain t. They can contain just a constant, for example, qt equals 5. They cannot contain anything other than t or a constant, however. Let's take a look at the homogeneous example. To see that it's homogeneous, we must manipulate it a little by factoring out a y and moving this term to the other side of the equation. Then we let pt equal negative t plus 1, and we've obtained the homogeneous form. Thus, this equation can be defined as a first-order linear homogeneous differential equation. For the non-homogeneous example, we first try to separate y and t, but it's impossible in this case. Notice we end up with pt equals negative t and qt equals t. Thus, it's non-homogeneous, and we define this as a first-order linear non-homogeneous differential equation. Now I want to go over how to solve a first-order linear homogeneous differential equation in the most general case, and I hope this solution will give you enough to solve any specific example. To begin, we're going to use a method called separation of variables. Let's say we have a differential equation of the following form, and the first thing we want to do is separate the equation to a point where we have only t on one side of the equation and only y on the other side of the equation, and I'll do that here. Now we have only t's and y's on separate sides of the equation. We seek to integrate both sides, the left with respect to y and the right with respect to t. Then we can combine the constants after we integrate. Then exponentiate both sides to get y alone. Finally, we can denote the exponential of c as another constant, and it's typically denoted as a. And we're done. This function yt is our solution to the differential equation. Now I'd like to go over how to solve a first-order linear non-homogeneous differential equation in the most general case. To solve such a differential equation there are a few ways, but I'm going to show you how to by finding an integrating factor. Once we find this, we multiply it by both sides of the differential equation and then solve for y. We find our integrating factor by exponentiating the integral of pt, where pt is in our differential equation. To solve this differential equation, we must first find our integrating factor. Then we need to multiply it to both sides of the differential equation. Then we can FOIL the left-hand side. Now take a close look at the left-hand side. This is a very important discovery, and it's why using this integrating factor works. The left-hand side can actually be rewritten as the derivative of y multiplied by the integrating factor. Now let's replace that, and then we integrate both sides with respect to t. By the first fundamental theorem of calculus, we can write the left-hand side as just y times the integrating factor plus c, because we are integrating a derivative. Let's now move the constant to the other side, divide our integrating factor, and simplify. Finally, we have found a general solution yt where c is just a constant and capital PT is just the integral of pt. Also note how I've cancelled out the a's in the first term and how I just merged c over a to be another constant c, because a constant divided by another constant is just a new constant. And we are done. We have just solved a non-homogeneous first-order linear differential equation in the most general form. To finish up the video, I'd like to go over a real-world example. Suppose that you're making coffee and by the time it finishes brewing, its temperature is 200 degrees Fahrenheit. Let's denote this as T0 equals 200. Suppose you're outside when you drink your coffee and it's a cold 45 degrees outside. Now clearly your coffee is going to cool because it's cold outside. Say this cooling rate is 0.03. This rate is dependent on many things. It depends on the material your cup is made out of, it depends on if you have your lid open, it's dependent on units of time. For our example, let's just let the rate be 0.03. In other real-world examples, if you would like to solve for our rate r, then you could measure the temperature of your coffee at 2 different times and solve for r, but for this particular example, let's just let r be given. Now you know that the perfect temperature to drink your coffee is at about 135 degrees. So how long should you wait to drink your coffee? This problem can be set up as a differential equation. The temperature outside is 45 degrees, the initial temperature is 200 degrees, the rate of change is 0.03, and we can denote the change in temperature of our coffee to be T prime over d capital T over dt. Finally, we can write our differential equation to be d capital T over dt is equal to Ra minus Rt. Let's interpret this equation. We are saying that the change in temperature of our coffee is described as the rate of temperature change multiplied by the area around the coffee minus the temperature of the coffee. And this makes sense because we expect the temperature of coffee to be cooler when it's exposed to the cold area around it. Now we seek to solve the differential equation. This equation is first-order linear and non-homogeneous, so let's use an integrating factor to solve. Since we've already solved the most general case of this type of differential equation earlier, I'll go through these slides a little faster. Now that we have a general solution of our differential equation, we want to use our initial condition to solve for the constant c. If T0 equals 200 degrees, then we set 200 equal to the equation for when all of our t values equal 0. Solving for c, we get c equals 155. Then we can plug that into our general solution. Finally, we want to answer the very important question, when should we drink the coffee when it's at a temperature of 135 degrees? Well, we need to set our temperature 135 equal to our equation and solve for the time t. Finally, t equals 18.12 minutes. So when drinking coffee, if it comes out at 200 degrees with a cooling rate of 0.03 and the temperature outside is 45 degrees, then you'll want to drink your coffee after about 18.12 minutes. That's all for me, and I hope you've gained a better understanding of differential equations. Again, my name is Kevin Roberts, and thank you for watching.